So now I think we're ready to start talking about quantum gates. If you recall from one of the earlier lectures where we were talking about classical gates, we were talking about how it would flip a bit in either the state 0 or 1 to the opposite. That was basically the long and short of how we could use gates in a classical circuit. However, with quantum, since each bit is given by this psi vector, where you have alpha and beta as the coefficients of the 0 and 1 state vectors, giving you a normalized state vector of alpha and beta, the goal of any given quantum gate is to transfer that vector, alpha, beta, to some other vector, let's call it gamma, delta. And the way in linear algebra that we make a transformation like this happen is through a matrix. So some matrix A, B, C, D. It might be helpful to review some linear algebra for this point, but essentially this gamma is going to be equal to A times alpha plus B times beta. This delta is going to be equal to C times alpha plus D times beta. If that sounds familiar, then you're on the right track. But essentially, we know that a quantum gate has to be a matrix. But not just any matrix. It actually has to be a specific type of matrix known as a unitary matrix. And the reason for that is because unitary matrices allow the preservation of a normalized vector in addition to a couple other useful things. So what is a unitary matrix? First of all, a unitary matrix is square, meaning its number of rows is equal to the number of columns. Also, its conjugate transpose is also its inverse. So let's say we have a unitary matrix U times its conjugate transpose, which essentially is a transpose of a matrix, and you flip the signage on all complex numbers. So I'll write that out in just a second. Equals I. So that means it's its inverse if it's equal to the identity by multiplying the product. This star means the conjugate transpose, and the conjugate transpose means that any complex number of the form A plus BI would become A minus BI, and you would transpose it as you would a normal matrix, and that's something that you could probably just look up. And finally, the magnitude of the determinant is equal to 1, and that helps this normalization happen. So a quantum gate is a unitary matrix. We're going to take a look at a couple examples. Hopefully this makes sense why this is the case. So the first type of gates we're going to be looking at for quantum gates are the polygates, X, Y, and Z, or Z, depending on where you're from, I guess. Just for this first one, let's just verify that it's a unitary matrix, and then I'll leave it up to you to show that that's true for the other two. So for X, of course, it's a square. It's a 2 by 2, so square, that's true. Now, its conjugate transpose, if you transpose this, you just put a diagonal line across it, flip it over, so it's exactly the same. And then this 0, 1, 1, 0 times 0, 1, 1, 0 is going to be equal to 1, 0, 0, 1, which is, in fact, the identity matrix. And finally, let's just check to see that the magnitude of the determinant is indeed 1. Well, 0 times 0 is 1, minus 1 times 1. Sorry, 0 times 0 is 0, minus 1 times 1 is negative 1. Magnitude of that is indeed 1. So we verified that this polygate is, in fact, a unitary matrix. Now, let's talk about what this X gate actually does, because this is supposed to be a practical thing, so hopefully we can see practically what it does. Well, let's just take the state 0, which, as a reminder, is 1, 0, and let's put an X gate in front of it. So that would mean, do this, 0, 1, 1, 0 times 1, 0. First row, 0 times 1 plus, so rather 0 times 1 plus 1 times 0 is 0. 1 times 1 plus 0 times 0 is 1. You'll see that that is 1. And maybe you can show yourself that x1 is 0. Now, this is familiar. It's actually just the NOT gate. which is helpful because we've historically expressed that as an X anyway. So the poly X gate is in fact the NOT gate for a quantum bit. The Y gate, not so important. I personally haven't seen it used a ton. And the Z gate is semi-important. It mostly is just sort of used for certain types of circuits that you're constructing because of the Z bases, which we'll talk about in the next video. We'll end our discussion by talking about the Hadamard gate, which is represented by a big capital H. This is probably one of the most important gates in quantum computing, and you'll see why, hopefully, soon, or at least by the end of this course. Now, it's kind of a doozy to verify that this is a unitary matrix, but I would encourage you to try. I believe in you. I think that you can show that this is unitary if you put your mind to it. But let's just talk about what the Hadamard gate does to our two most sort of common states that we're dealing with, 0 and 1. So if you apply a Hadamard gate to the state vector 0, that's going to be 1 over root 2 times 1, 1, 1, minus 1 times 1, 0. So that gives us, in the first row, first row, it's going to be just a 1 over root 2. Simple enough. Second row, hey, also 1 over root 2. So we can write that in our sort of typical psi form as 1 over root 2 times state vector 0 plus 1 over root 2 times state vector 1. Or, if you want to simplify it even further, like so. And this is an interesting state because if you sort of calculate out probabilities like we did in a previous lecture, you would find that if a qubit is in a state like this, the probability of measuring it as a 0 or a 1 is in fact 50%. We've created an equal superposition using the Hadamard gate. And that's true always. If you have a sort of standard 0 or 0, 0 or any number of bits and you apply a Hadamard gate to it, you're able to actually create an equal superposition of all possible states that those n bits could be in, which is incredibly useful. Without going through the math again, I'm also going to say that Hadamard of 1 is equal to 1 over root 2 times 0 minus 1, which physically has no different observable outcomes from this state right here, because the probability of measuring either state is still 1/2, but the phase is different here, and we talked about that in a previous lecture as well. And it is important. So they're not the same, but physically they are kind of the same states. So something to think of, or rather for use of notation later on, we call this state plus and this state minus. And something useful is h of 0 gets you plus, h of plus gets you 0, h of 1 gets you 1, rather minus, and h of minus gets you 1. Another fun identity about the Hadamard gate, and this is something that I will leave you, the viewer, to demonstrate, is that if you wrap a Z gate in Hadamard's, you actually get an X. If you wrap an X gate in Hadamard's, you get a Z. Hopefully this was a good introduction to quantum gates. We'll obviously be using them a lot when we're creating quantum circuits. And the X, Y, Z in Hadamard are definitely the most important, and we'll bring up other ones as we go.